Alright, today I'll be talking about rotation, which is basically just something rotating around, a rigid body rotating around an axis. In this panel you can see this purple and this brown layer were rotated up, which is, just basically what they do, what a geologist does, he picks an axis, which would be my middle finger, and then decides whether it's counterclockwise or clockwise depending on the rotation. Like, I think this in your view would be clockwise, that'd be counter. So you just pick a rotation, it doesn't matter, like how it's orientated around, but you just pick one, you look directly down the axis, and you decide if it's counterclockwise or clockwise. That's basically what most of this stuff is describing, like the magnitude of rotation being from 0 to 360 degrees, so around the axis, 130 degrees, clockwise or whatever. And also, like, as layers are rotated, the net slip increases, and the net slip is like where this is all just one unit. It's saying like this has slipped that much from these joints have slipped that much from being in line, and then this one has slipped 2/3 of the way, and then this one has slipped all the way away. And those primary structures are a really good way of figuring out how much something has rotated. Like here you see like the pillow basalts. We know that this rotated, looks like counterclockwise, I don't know, like 90 degrees, something like that. Oh yeah, counterclockwise 90 degrees. Yep, and down here I wrote some listic normal faults, and these are the spiral grains can form like as things are rotated. Like in here there can be like little circular grains that form around the rotation that can also tell you the direction and intensity of rotation. Next is strain, and it results from a non-rigid body deformation through dilation, changes in size, or distortion, changes in shape. So this can be seen through the changes in the spatial relation of points within an object. So pure dilation can be seen in the drying of mud or cooling of basaltic lava. Like as mud dries, it starts out with the water having the pores, it's about that big, and then as it dries, all the water in the air escapes, and so it just kind of keeps its shape but shrinks. And the distortion can be seen when just one shape changes from another, like if you have like a square changes into a circle, or just it's the same area but it's a different kind of shape. Transformation, deformation, and strain. Deformation, the collective displacement vectors of a point within a body, is the three-dimensional transformation from initial to final state. Strain is a part of deformation along with rotation and transformation. So remember that the displacement vectors aren't the same as the displacement paths, where the displacement vectors go from x, y, and z to x, y, and z prime, and the paths are how it got there. Homogeneous deformation, lines that were straight before deformation remain straight, and parallel lines remain parallel. So it's basically like a perfect circle changing into a perfect ellipse, or you'll be thinking of strains in mostly 2 dimensions. In this class we decided to just kind of keep it in like a 2-dimensional strain, just to simplify a lot of the explanations. So no matter how many times the perfect circle undergoes homogeneous deformation, it will be transformed into either your perfect ellipse or back into a perfect circle. So it's basically saying like if a perfect circle gets squished, then it's a perfect ellipse, and if that perfect ellipse gets squished down again, then it's a perfect circle or another perfect ellipse, as long as the deformation is homogeneous, which means like the same in all directions or in the same direction. But in geology, perfect shapes usually aren't very common. You usually measure it by like the lengths of lines, the changes of angles, and between those lines that were originally parallel, or finding the difference in angles between things that were perpendicular, just kind of figuring out how things changed. So down here, describing changes in lengths of lines, we have extension and stretch, where extension is basically like the percentage of change that it underwent, where you do the final minus the length of the initial divided by the length of the initial, which gives you a percentage. So this one would be like 60%. So it like means that the line experienced a 60% growth, like it changed, like it gained that much. Like 8 minus 5 divided by 5, 8 is 6% larger. So stretch is the amount that it's actually stretched or changed. So like this is like 8 over 5, it's 1.6 times longer than it would be, which would be something that you would probably do on like grand scale stretch and extension. Probably won't spend too long on this. Inline, yep. X length to deform fossils, measures up all the pieces. Oh yeah, so like this is like if a broken fossil, like was right in here, you measure up the pieces like, whatever that is. I think that's 70 plus 10 plus 30 plus 22, whatever it ends up being. The initial length is 82, and then the final length, which is the total length over this whole area, is 185. So the extension was 1.3 or 130%. So we know that the rock was stretched by 130% as well. This is a good tool in finding the stretch of a rock unit. So like you'll just know that if this is one fossil basically broken up into 4 different pieces, that one fossil after it broke was stretched further away. And so you not only know how big that fossil is, but like originally that fossil was this long, and then as it got broken up, now the ends of the fossils are out here. So that's just basically a way to kind of figure out how much change has this rock unit has undergone. The benefit of making a cross section of a rock unit is to be able to tell the extension and stretch that it underwent. That's true. Okay. Line length changes when a circle becomes an ellipse. So like this is basically like a worm burrow that's pretty common in a lot of rocks, and like the worm burrows are usually pretty good perfect circles, and if you're able to like figure it out from like this perfect circle of a worm burrow to like how it became an ellipse, then you'll be able to know the amount of stretch and strain in that. And that's by the area of an ellipse is pi AB, A being a major axis and B being the minor, and equals pi r squared, which is the area of a circle, interior radius and deliciousness. Alright, so like here is just an example of like how you find it. Like B is 2.2 centimeters, A is 2.6, so you just divide those by 2 because you're finding the radius. 1.3 times 1.1 equals 1.4, which is so that'd be like pi times 1.4 is equal to pi times whatever radius is squared. And so then you divide the pi's out, so 1.4 equals radius squared. 1.4 squared, or the square root of 1.4, is the radius of the original circle. And then you use that radius of the original circle, and you just basically figure out, the extension and stretch from there. You can, if you're interested in it, you can just kind of check it out in here. So like final minus initial, that kind of stuff. Of major axis, minor axes is all in there. If my mouse will work. And here's the final, like line A underwent a extension of 8.3% and a stretch of a factor of 1.1, and line B underwent compression of 0.92 and a shortening of 8.3%. It's a good example of finding a feature in a rock and gauging some information, some on-the-spot knowledge. So angular shear is basically just how something shears on an angle. It's pretty self-explanatory. It measures the changes in angle between lines. Angular shear, which is this like little pitchfork symbol, changes that take place in angles between lines. is described by the change that a line has to on that is parallel to it originally. So it's the change in the angle that a line has to where another one that is perpendicular to it originally. So like basically, like how this one is perpendicular to the x-axis. When we do angular shear, clockwise is negative and counterclockwise is positive. So from horizontal, this line has an angular shear of negative 50 degrees. And usually are accompanied by changes in length and shape, just because if you change the orientation of a feature, usually you're going to change some of the other characteristics of it. And fossils are always a good way to measure, like, just anything that you know what the original shape is, which is like fossils or those burrows, is a really good thing to gain information from. Like, if you know a trilobite fossil was this big and it was, shaped like this, then you're able to kind of figure out, oh, well, if half of the trilobite fossil is now up here, well, then that's where the rocks moved, because, the trilobite fossil is unknown. So, shear strain, which is gamma, if the deformation is homogeneous, we are able to find out more about the movement. I think I might actually be able to flip this to where y'all can see it. What is it? You want to rotate it to the left. Sweet. So, like, basically this is, like, saying that if the deformation is homogeneous, like, you figure out the tangent of the shear, of the angular shear, and that should equal the gamma or the shear strain. So like right here, it's went over. This is evenly spaced, so this is went over 0.5. So gamma is 0.5, and this one has went over 1 full unit. So it's 1 in relation of that shear. Oh. Just gonna have to go all the way around now. Alright, kick ass. Oh, is that it? That's it for now? Yeah, this was it that I was gonna do today. So I guess I'll just kind of try to go over shear a little bit more. Like, the angular shear, you're figuring out the component with just basic trigonometry. Like, the tangent of this is equal to the changing component of x over y. So that's just showing you how much the unit has actually moved. And like I said before, like, the fossils are a really good way to figure that out. Yeah, I think I'm gonna be good for